Hello, welcome to the podcast On Consciousness with Bernard Baars, open-minded conversations on some new ideas about the scientific study of consciousness and the brain. I'm Nat Geld, this show's producer. We're here today with Bernie Baars, acclaimed author in psychobiology, including his newest book called On Consciousness, Science and Subjectivity, Updated Works on Global Workspace Theory. Bernie Baars is the originator of Global Workspace Theory, GWT, a theory of human cognitive architecture, the cortex, and consciousness, and he is one of the founders of the modern science of consciousness. First, we want to thank you, our listeners, for tuning in with a 50% discount for any edition of Bernie's new book, On Consciousness. Just go to shop.thenautiluspress.com, and I'll spell it, shop.thenautiluspress.com, and be sure to enter the word BOOKS, BOOKS, in the coupon code box during checkout for your 50% savings. Of course, they're available everywhere books are sold, although your VIP discount is only available in the Nautilus shop. This episode features two interesting student interviewers. Alia Squara, a PhD candidate at Sarin Lab, Center for Mind and Brain at UC Davis, and a cognitive science student, Ilian Daskalov, from UC Irvine. Ilian, and Bernie Baars will discuss his global workspace theory, GWT, which began with this question. How does a serial, integrated, and very limited stream of consciousness emerge from a nervous system that is mostly unconscious, distributed, parallel, and of enormous capacity? In this episode, Part 3, we'll explore how we can understand the evidence of various brain implications of the theory and unpack global workspace functions. Hi, Ilian. Hi, Alia. Welcome. Okay, now, before I hand over the mic to y'all, we'd love to learn a little bit more about each of you, please.
All right, thanks, Nat. Briefly, I'm going to introduce myself for anyone that did not hear me in previous episodes. My name is Alia Squara. I am a PhD candidate in psychology at the University of California, Davis. I study compassion and responses to suffering in the context right now of intensive meditation training. And I am here today, as I have been for the past several episodes, to talk with Bernie and with Ilian about consciousness, and specifically about the global workspace theory and different pieces of evidence that help us understand how consciousness might work both theoretically and in the brain. I'm going to pass it off to you, Ilian. Hello. Good morning.
Good morning, Ilya. It's a pleasure indeed, and good morning to our listeners. My name is Ilian Daskalov. I am a senior at UC Irvine, where I study cognitive science. I am deeply interested in the topics of sleep and consciousness, which is great because this is what we'll be covering today. And it has been a great pleasure to talk about consciousness, especially in the past two episodes. And I briefly wanted to just summarize what we discussed so far. So if you don't mind, I'll just take us on a journey through the previous two episodes. And the first episode is where we explored the beginnings of Bernie's global workspace theory, which was initially ignited by the strictly behavioralistic mindset of the majority of the scientific community at the time. Additionally, in the same episode, we also discussed some of GWT's features, such as limited capacity, or our ability to be consciously aware of only a very small part of all events that happen in our brains. And finally, we discussed global workspace theory's main hypothesis, which is widespread integration and broadcasting. We defined widespread integrations as the ability to perceive a mistimed sensorial information as a signal event. And we also define broadcasting as the ability to hyperfocus on a narrow piece of experience. For the next episode, which is episode 17, is where we delve deeper into some of the cutting-edge brain evidence and how that supports or updates our understanding of consciousness and global workspace theory. We started by talking about Bernie's 2013 paper, which is called Global Workspace Dynamics, Cortical Bindings and Propagation Enables Conscious Contents. And that paper is a result of 4 decades of cumulative work. So it's a very essential piece of work of what we discussed in that episode. We then examined some of the best empirical confirmation there is out there. We looked at a paper by Gaillard et al., and that strongly supports the global workspace hypothesis that sensory consciousness involves a multi-source convergence in a visual cortex, which is then broadcasted to the intertemporal and mediotemporal lobes. And finally, we then examine an additional 3 other papers which support Bernard's global workspace theory even further. And all of that leads us to today's conversation when we're going to talk about sleep. But before we get into the nitty-gritty of sleep and the neurobiology of it all, why are we talking about sleep, Ilya? And why is it so important to consciousness?
Yeah, so like Ilian said, we are in the 3rd episode on our mini-series of Global Workspace Theory. So if you haven't listened to the first 2, I suggest you pause here, go back. Ilian just gave us a great recap of episodes 16 and 17. I would take a listen to those and then join us right back here. So like Ilian said, today we're going to be discussing what happens when we fall asleep. When we fall asleep, consciousness fades, yet the brain doesn't go to sleep, it remains active. So why is this so, and what could that teach us about consciousness? So Ilian, I'm actually going to punt that question you just asked me right on over to Bernie. Good morning, Bernie.
Good morning.
Good morning. Tell us a little bit about why are we talking about sleep today? How is that relevant to consciousness? What are we going to learn here?
Well, I don't know why you're talking about sleep, Ilian. I'm talking about sleep, I guess, because, well, first of all, because it's the most prominent example of an unconscious state, or what appears to be an unconscious state. And I think pretty much every single culture in human history has had words for waking and sleep, and lots of other words, of course, for mental processes. Like, wake up, you lazy bum. It's time to do some work. Or it's time to, milk the cow and get the eggs from the chickens. Anyway, we always, I think as scientists, we tend to forget the ordinary human experience, which is all about consciousness and something more, of course, about dreams and about the imaginary world that every single culture creates and updates and follows. So those 3 domains, I think, of waking consciousness, which is reality-based. Freud was right on the reality function of consciousness. It is at least one of the functions. And then there are these 2 domains of fantasy, dreams being one of them, and of course, waking fantasies, which turn into myths and narratives and enormously important things, right? That the popular view is that these things are projected onto reality by people. And so they reflect people. Anyway, all of those states are crucial for human beings. And so waking is clearly involved with coping with reality because, if you're a hunter-gatherer and you're a child and you're not awake when the tribe is going off to the hunt in the morning, you're not going to be happy, and nobody else is going to be happy about you either. So consciousness it's something that we all talk about. We call it attention, right? And attention brings about consciousness of whatever it is we want people to pay attention to. So those things are intertwined. And the role of reality and fantasy has been coming up back for me. Of course, it's been around forever. But the role of reality and fantasy corresponds actually pretty closely to waking and dreaming. Anyway, that's just a little introduction from my point of view.
Thank you, Bernie. So yeah, it's these kind of different states that we all cycle through in our day. And as Bernie alluded to, there's waking, where we're kind of processing all of this external information. And then there's everything that happened during sleep, including dreaming, which I don't think we're going to get into too deeply today, but we are going to talk about our different phases of sleep and what goes on in our brain. I think a feature, like Bernie mentioned, of sleeping is that we're not attending to things in our sensory environment in the same way. Maybe we're dreaming, maybe we don't have any awareness of what's going on, but our brain doesn't just stop working. So historically, there are philosophers thought that maybe the brain went to sleep, that it became less active during sleep. Is that right, Bernie? Am I kind of getting my history of philosophy and science there?
Every opinion in the land on that. But I think the real question is, what is it actually that the brain does do in waking, dreaming, and sleep?
Yeah. And so we're going to get into that a little bit today about what happens in the brain during different stages of sleep and what can that tell us about conscious experience when we are waking. So before we start to dive into all of the two papers we're going to get into today, I'm first going to tell you a little bit about the primary author for these papers we're going to be discussing. So in this episode, we're going to discuss two papers by Marcello Massimini. He's an MD and a PhD, and he's a professor in the Department of Biomedical and Clinical Sciences in Luigi Sacco at the University of Milan, Italy. So his research has some compelling evidence from studies in the sleeping brain that provide some insight into the cortical dynamics that could underlie conscious experience. So this ties back to some of what we discussed in episode 16 and in 17 about what is consciousness, how does the brain support this experience. So a little bit about Massimini. His research is devoted to understanding changes in thalamocortical networks when consciousness fades and then recovers, such as when we sleep and then reawaken, again, like these cycles that Bernie was talking about. In addition to the neurophysiology of this, Massimini is really interested in the theoretical and philosophical implications of neuroscience and consciousness, and those are the main questions that his lab studies. In his pursuit to understand the brain dynamics of consciousness, Massimini performed some of the first high-density EEG recordings in sleeping humans and was able to describe the spatial and temporal dynamics of slow sleep oscillations. So the first paper we're going to discuss today is actually looking at these slow oscillations that occur during sleep, and we'll talk about what an oscillation is. And then he focused on developing novel techniques, pairing something called TMS and more EEG recordings, which again, we'll define what each of those are in a minute here, to study cortico-cortical interactions. And using this approach during wakefulness, sleep, and dreaming, different types of anesthesia, brain injury, he demonstrated that consciousness is tied to the brain's capacity to integrate information. Those are a lot of terms we just threw out. I promise we're going to get more in depth for each of those. But overall, these experiments just shed new light on potential mechanisms of consciousness and consciousness loss and recovery, and give us some insight into what it is in the brain that might be correlated or relate to our conscious experience. And so this includes, there has a pretty broad implications, including being able to classify and understand non-responsive patients, like someone who's in a coma, understanding what's going on for them in terms of their experience or potential capacity to recover, in addition to the philosophical and kind of basic scientific implications for understanding the nature of consciousness in the human brain. Bernie, before we jump in, why would it matter to be able to index someone's consciousness for these patients? I think that's kind of sometimes one of the most important, or most, maybe not important, but one of the most immediate.
No, it's actually the most important. So
there we go.
Thank you for raising that question. Do you want to complete the question?
No, go ahead. The question is, how could this help us help non-responsive patients? Why would this matter?
I see. So non-responsive patients, some of them are actually conscious, as you know. It's historically been very, very difficult. Essentially, what doctors used to do is if they had a non-responsive patient and you didn't know how to find out if they were conscious or not. So all the doctors would come over and over again to the patient and pinch their thumbs. And the resulting condition, I think it was called purple thumb syndrome, because they kept on doing it. And if they didn't get a response, they assumed the person was actually unconscious, right? Unconscious coma. but there is a category of conscious coma. And those people were particularly unfortunate in what was called the locked-in syndrome, which is like being locked in and you're conscious of everything around you in the normal way, but nobody knows that you're, yes?
But you can't respond. So you're having conscious experience, but you can't communicate that out.
Yes. Go ahead on that, by the way. Just take off if you have something to say.
Oh, just clarifying that. So when we talk about locked-in syndrome, I think this is really interesting for consciousness, that someone can be aware of their experience, they can be taking in this information, they can be integrating it, they can be having an experience and be completely unable to communicate that to people around them or to actually respond in a visible way with their body to their sensory environment, even though inside their brain, they're having a full experience of it. And so that, you can imagine, would be a really terrifying experience, and also one that before these studies of consciousness in the brain, we from the outside wouldn't be able to distinguish from someone who truly had lost all experience.
Is that in any way related to sleep paralysis?
Oh, interesting question. I think those are different mechanisms. Usually a coma would be with brain damage versus sleep paralysis is when you go to sleep, there are hormones that are released in your body to immobilize you so that you don't fall out of a tree, right? So you're actually paralyzed, but your brain wakes up while your body is still paralyzed and you're not able to move. I'm not sure about the exact neurotransmitters or mechanisms of that, but that's my understanding of sleep paralysis. It's where you kind of become aware or conscious in a more quotidian, daily sense, like Bernie was talking about, but your body is still in the immobilized state of sleeping. Is that your understanding as well, Bernie?
Yeah, one of my far out thoughts about that is that the dream journey of shamans, who are extremely widespread throughout many cultures, many tribal cultures, their dream episodes involve a feeling of being dead, basically. And that may seem weird, but it's actually not so weird because we normally go into sleep paralysis, and then normally, of course, we don't know it. But we can dream about our own sleep paralysis. And I have to remind you that sleep paralysis is entirely normal and desirable. So there's nothing wrong with it. But sometimes, if you notice that you're trying to move your body in your dream, and it doesn't move, and you say, holy something, and you're a shaman, right? And so this becomes part of your spirit journey, which is really fundamental. It's shamanism is this really cross-cultural phenomenon, stunningly similar in different, mostly hunter-gatherer cultures.
Yeah, we see across cultures too this interest in these transition states, and sometimes, as neuroscientists, we understand them as transitions between different brain states. In other worldviews or cultural times, you understand them as transitions between the spirit world and the physical world. And in some ways, all of these things relate to and kind of speak to the importance of these transitions between different ways of experiencing different states of consciousness and how much that kind of universally speaks to the human experience.
Speaking of different states of the human brain, I wanted to pause back a little, and can we just talk about what exactly happens when a human falls asleep? I'm sure most of our listeners know that we go through different stages throughout the night of sleep, but can we just briefly touch on those stages and how they differ and what exactly happens in the brain?
Yeah, absolutely. So before we dive into the nitty-gritty, I have done some research for us to discuss a little bit the different stages of sleep. So this is not my area of expertise, but it's something I really enjoyed learning about for this episode. So, Ilian, like you said, we don't just go from being awake to being asleep. There are actually stages of sleep that we cycle through. And so you may have heard the term a sleep cycle. So what does that actually mean? So sleep can be broadly divided into REM sleep and NREM sleep. NREM sleep literally just means non-REM. So during REM sleep, REM stands for rapid eye movement. So this is kind of the last or deepest stage of sleep where your eyes are rapidly moving back and forth. That's how it gets its name. And this happens for about 20 to 25% of the time that you're sleeping. So REM is kind of the final stage in a sleep cycle. Before you reach REM, you go through non-REM sleep, and this is divided into, again, several different stages. So the vast majority of our time that we are sleeping is spent in NREM. It has 3 stages, N1, also referred to as stage 1 sleep. And this is kind of the transition between wakefulness and sleep. So this kind of twilight space where you're starting to fade. N2, which is also referred to as stage 2 sleep. This is kind of light sleep, and adults spend about 50% of their sleeping time in this stage. And then there's N3, which is also referred to as stage 3 sleep. This is also called deep sleep, slow wave sleep, delta sleep. You may have heard it referred to as all those names. And then REM is sometimes referred to as stage 4 sleep. So when you go through a sleep cycle, it typically begins with NREM, where you go through all of those phases of NREM, so phases 1 through 3, and then it'll transition to REM. And a full sleep cycle generally lasts for an adult between 70 to 120 minutes. So a typical adult will generally go through 3 or 4 full cycles from NREM to REM back to NREM in a night's rest. One quick side note, the definitions of the stages of sleep were actually updated by the American Academy of Sleep Medicine in 2007. So before which, sleep was generally divided into 5 stages. And both of the papers we are going to cover today were actually published before this redefinition. So they were published in 2004 and 2005, respectively. So their stage definitions don't always align with the current definitions of sleep stages. So rather than referring to specific stages, we'll talk about light sleep, deep sleep, which remember are both phases of NREM sleep. And then we'll talk about REM sleep. And that will translate well enough. So just a quick little disclaimer there that actually the stages have been differently divided since these papers were published, which I thought was super interesting.
Down the line, I would like to ask you, because there's constant debate about these things, of course, what the current state of our understanding is of whether dreams and REM are actually the same thing or not.
Gosh, I wish I knew. This is not my area of expertise, and so I am not sure where dreaming kind of falls into this or how that's defined. Do you have any idea, Bernie?
I don't know what the state of the art is right now. My own guess is that dreams are fully conscious states, but you know perfectly well that experimental people live to pick gnats. Is it gnats? Whatever you pick. And they're very, very good at details. They're constantly coming up with new insights. So I'm curious about the current state of that question. It's such a fundamental question, right?
Yeah, and I do think most of your dreaming does occur during REM sleep, which is interesting when we get into these papers, because most of them are looking at the fading of conscious experience and NREM sleep. So again, we're going to be talking about these non-REM phases where you do both experientially, and it seems like, as we'll cover neurophysiologically, see these correlates of consciousness fade, and these findings actually don't apply to REM. So things look quite different in REM sleep, which is interesting when we start thinking about dreaming and its relation to conscious experience and brain activity.
Right.
Ilian, I know you're really interested in sleep and dreaming. Did you have anything you wanted to chime in on here?
I'm not that familiar with dreaming and the connection with REM per se, but I feel like where you left it off gives us a very good segue into the papers. You mentioned that you want to define oscillation, and I feel like that would be a good moment to do that right before we get into the papers.
Yeah, absolutely. So before we dive into the papers, like Ilian said, we're going to be talking about a number of different neurophysiological features or experiences. And I think it's really important to understand some terms. And the most important one for understanding these papers is the idea of an oscillation. So if you are watching the recording of this, I'm going to go ahead and share my screen where I have some pictures. And if you're just listening, I will describe these as I talk. So right here, as I have on my screen, is an image of what is called an action potential in a single neuron. So if you're just listening along, essentially what you see is a waveform. It goes up and then it goes back down. So the basic unit of communication in our brain is the firing of a neuron. And the way these neurons fire is through something called depolarization, which basically means that there's a shift in the electrical potential between the inside and the outside of the neuron. We don't need to get into all of the kind of sodium potassium channels that are involved in that. We can talk just about the idea that for a neuron to fire, which means for it to release its neurotransmitters to send a message to another neuron, it has to depolarize. So essentially what happens is that this neuron changes its electrical potential due to input from other neurons, or as we'll discuss later, from TMS, and its membrane potential. So this membrane has a resting potential. It crosses a threshold. Once it crosses a threshold, it's a 0 or 1 thing. If it crosses a threshold, it's going to fire. If it doesn't cross the threshold, it's not going to fire. So we see this crossing of a threshold, which then we call an action potential, where it depolarizes. The signal is transmitted along the length of the neuron, and then it repolarizes and goes into what's called a refractory period or a hyperpolarized period. So when we're talking about those papers, you'll be hearing about depolarization. So remember, that's when neurons depolarized fire are active. So you can think about that as neurons are firing. And then they go into this phase of hyperpolarization, where they actually can't fire. So they're quiet. They're not talking. And again, this is at the level of a single neuron. We see depolarization, neurotransmitters released, hyperpolarization or refractory period, neurotransmitters can't be released, back to resting state. Then they can potentially, if they receive the input that tells them to fire, depolarize and fire again. So that happens at the level of the individual neuron, but what are we talking about when we're talking about an oscillation or a wave? We're not actually talking about a single neuron. We're talking about the activity of assemblies of neurons to create these oscillations or waves. So there's not a one-to-one relationship, particularly when we're measuring signals at the scalp, between neuronal firing and an EEG wave or an oscillation. But there is, the relationship is kind of dependent on the volume of neurons in a particular area that are firing. So remember, I said there is a change in the electrical potential of a neuron. So it has to exchange ions with somewhere. Where is it exchanging those ions with? Well, it's exchanging them with the extracellular space. So when a neuron is depolarizing, it's exchanging ions with the space outside of its cellular membrane, in the extracellular space. If you have a bunch of neurons doing this all at the same time, so if there's an assembly of neurons in a particular area of your brain that are all depolarizing at the same time, that actually causes enough of a shift in the charge of the extracellular space that there's a change in what is called the local field potential, and that is the charge of the extracellular space. So when we see these changes in local field potential, what I'm showing a picture here for those of you who are looking at how that relates to neuronal spiking, so neurons firing. But again, if you have a bunch of these neurons firing all at once, you'll see this change in the extracellular potential. It then recovers, neurons fire a bunch more, then you have a change in the extracellular local field potential, and that is actually creates this oscillatory or wave shape, this shift in the local field potential.
Yeah, you want to remember the root word of polarization and hyperpolarization and this and the other thing. There are two values, right? For the inside and the outside of the membrane, either at minus or plus, just like a battery. And that's called polarity in electrical stuff. So everything comes down to the two poles, the North Pole and the South Pole. in this case, the negative pole and the positive pole. And what gives the power to the neuronal signaling, because you need power to push that thing, right? And to push it quite rapidly, actually. You get it from the sudden inrush of the external ions and the outrush of internal ions across the membrane. And then that essentially shoots off the whole signaling system. So I just want to remind you about the word polar.
Thank you, Bernie. Yeah, that's very important. So when we're talking about polar here, we're essentially referring to the difference between the internal and external space of a neuron. So the intracellular and the extracellular space, and these changes in charge or potential. So remember, depolarization, neurons are firing. Hyperpolarization, neurons are not firing. And again, that causes a shift in the local field potential or the extracellular space around those neurons. And then that can be recorded either close to those neurons by sticking an electrode all the way into someone's brain and recording from the extracellular space in a particular area, which is called a depth recording or a local field potential recording. It can also be recorded from further away with what's called a grid recording, or a strip recording, which are actually placed on the surface of the brain. So you still have to have someone's head open to do these sorts of recordings, which is not typically what we do, right? You need a pretty good reason to cut someone's head open. So most of our recordings in humans are at the scalp, and this is EEG, recording of the shifts in electrical potential at the scalp. So by the time we get to EEG, we're not recording the firing of individual neurons or even groups of neurons, and we're not even recording the local field potential because we're too far away. But what we are recording is the signal of many local field potentials layered with each other. So we're getting this complex waveform of all of these local field potentials occurring all over your brain and then propagating throughout this big saltwater bubble. Basically, you have this jar of saltwater jelly that is your brain, which propagates these electrical signals all throughout your brain and across your scalp. And then we can record them at the head. So when we're using EEG, we're using these sensors. We're not putting anything into your brain, right? With EEG, we're only recording what's coming out. And we're recording these electrical signals at the scalp that are these complex waveforms that are created by this fluctuation of field potentials throughout your brain. Bernie, does that cover EEG for you? Do you want to talk more about what EEG is?
It does. I think you have to remember, in addition, that humans have thick skulls, and we're very different from your kitty cat in that respect, or from mice, which are actually very similar to kitty cats, and have very thin skulls. So you can pick up electrical activity in those critters a lot more easily than you can do it in humans. And for a long time, this was not sufficiently appreciated. And looking back, that seems pretty bizarre, because anybody that works with electricity knows, if you have to go through a solid wall, which is what the skull is, it's bone and blood vessels and all kinds of tissue. And the loss of signal between the cortex, you have to remember that single neurons fire around minus 60 millivolts. So that's millivolts, a thousandth of a volt. But from the typical EEG outside of the human skull, we only record microvolts, and that's 1,000-volt drop in signal. And so the traditional view of that is that it's close to impossible to read minds through the EEG. And it turns out to be scary that it's no longer impossible, but it's also revealing. It's scary because it's revealing, right? And so it's really important for scientists to understand the critter that we're working on or that we're talking about. Humans have thick skulls. This is an easy one to remember because we're constantly complaining about that fact. Other mammals and creatures outside of the mammals, most of them, except for whales, right, have quite thin skulls to the point that you can actually, if you shave the fur off a mouse skull, you can probably see the blood vessels, I think. Is that right? Do you think so?
You know, I'm not sure. I've not done mouse research, but it's certainly true that humans have this incredibly thick protective skull in addition to the hair, right? And then we have this thick skull, we have our derma, like I have actually very thick dura matter, or, you know, you have like the tissue on top of your head, like different people have all of these things that by the time we get to recording at the scalp, we're getting, again, not just information from the brain, but we're also getting muscle and this propagated signal across our scalp. And it's very, like Bernie said, attenuated. So we're getting just like a minuscule, tiny little signal compared to everything that's going on in the brain. And yet it actually can offer really compelling information about what's going on.
So how does that relate to the first paper we want to discuss, specifically brain waves and slow brain waves?
Yeah, thank you, Ilian. So in this first paper we're going to discuss, this is a paper by Massimini, who we discussed earlier, gave a little intro to, Huber, Ferrarelli, Hill, and Giulio Tononi, who's a well-known researcher in consciousness studies. And so this paper is called, let me get the label here. So this paper is called The Sleep Slow Oscillation as a Traveling Wave. And so this paper starts with the observation that during slow wave sleep, a dominant feature of neural activity is, as you might guess, a slow wave. So remember, if we turn to understanding of how a neuron fires, we see this happening, this wave form happening across the whole brain. So what they wanted to know is whether these slow oscillations, and when I say slow, I mean about 1 hertz, which means about 1 oscillation, about 1 rise and 1 fall per second, which is comprised, like we talked about, of a hyperpolarized or down state. So hyperpolarized, neurons not firing, but again, this is happening across the whole brain. So this hyperpolarized state where virtually all neurons in the brain are quiet is what was thought about this down phase of this slow wave, followed by a depolarization or up phase that lasts for several hundred milliseconds. And during this, the membrane potential surges back up to its firing threshold, and the entire or a large part of the thalamocortical system is just firing with this huge amount of synaptic activity that's actually greater than what we observe during quiet wakefulness. So this is observation of this slow wave in the brain during slow wave sleep. And what they wanted to know is whether these slow oscillations are happening in synchrony across the whole brain at the same time. So is it that the whole brain is hyperpolarized and quiet, and then the whole brain is depolarized and firing and active? Or is it actually a wave that's traveling across the cortex? And now Bernie's point about the thickness of the skull and the conduction is really important here, because remember, our brain is a really good conductor. So when we're looking at EEG recorded at the scalp, when we have a signal in the brain, it immediately propagates throughout the brain across the whole scalp. And so it can be really difficult to tell whether this is happening everywhere at once, or whether that's just a result of the conduction of the signal through the brain, and whether it's actually happening in different areas and kind of getting passed along. And so that's what this paper is essentially asking is the slow wave we observed this unitary phenomenon, whole brain quiet, whole brain active, or is it something that's traveling from brain region to brain region across the brain like a wave? Does that make sense?
I think, well, it makes sense to me. There is this consequence of the thickness of the human skull that is, I don't know if it's really emphasized these days, but it's really important. Because what you pick up from cortical electrodes, right, deep electrodes, right on the cortex, close enough anyway, what you pick up is what's called buzz-pause activity, or at least that's what it was called about 10 years ago. And I need you guys to tell me if, what the current state of the science is, because the scuttlebutt about 10 years ago was that the cortex is going buzz, pause, buzz, pause. And what showed up at the outside of the scalp, which is usually what you think of when you're watching people have an EEG, is these slow oscillations. So slow oscillations could be, and I don't know the answer, an artifact of our, formidably thick skulls. And there's interesting questions about why do we have such thick skulls, human beings, as opposed to cats and dogs and mice and stuff like that. And we can speculate on that. It's a very important question, actually. What's the Darwinian benefit of having these very, very thick skulls? Do you think it might be, to play football or to
survive better if you get hit on the head?
Yeah.
I mean, we spend a lot of energy making our brains. Our brains are like very expensive, so it makes sense that we want to protect them.
Yeah.
Yes.
They use so much energy from the total energy we use on a daily basis.
Yeah, I really would love to hear from you guys at some other time. What's the cost benefit of having this enormous brain, and especially when it's conscious, of course, during the waking period, and also the dreaming period looks very much like it's like the waking period. What's the cost benefit of that? Because the cost is enormous, as you guys just said, right? And we sort of can guess about the benefits, but it's still important for us to understand the benefits.
Yeah, I think that'd be a whole other discussion could be really interesting about, I guess it depends on what your priorities are. What are the benefits of consciousness?
Mm-hmm.
So I just wanted to ask you, Bernie, so Aaliyah summarized the paper really well, but I heard some things that I personally related to what we previously talked about, global workspace theory, and especially the dynamic hub of things. Would you care to explain how the paper Aaliyah just summarized ties up with global workspace theory and some of the features?
Well, I think we actually have to get into the data still. Bernie, if you want to talk about why the slow wave might matter.
Oh, sure, but not now.
Maybe after?
Follow the plan. Yeah.
Okay.
Mm-hmm. After would be fine.
Let me share my screen again. So I'm going to quickly tell y'all about the methods. Okay, so are you all seeing just a picture of
Waves?
Waves? Beautiful. Okay, so in this study, like we said, they're interested in understanding if this is a single slow wave happening in the whole brain at once or whether it's traveling. So to do this, they had participants come to the lab to sleep. And they had them come to sleep for one night, 1 week apart. So they have 2 nights of data on each person. And what they did is they recorded EEG in these participants while they slept in the lab from the moment they kind of laid down and were in this wakeful state in the transition into the deep sleep. And then they used an algorithm to detect these slow waves. So what you're seeing here basically in this depiction is the locations of the electrodes on people's head with the brain projected underneath. Then you have this complex waveform that we talked about is this combination of muscle activity, of brain, of the propagation of that signal throughout the brain. And then they used an algorithm to turn that complex signal into this slow wave detection. So every time you see a star is where this algorithm detected a slow wave. So that's the method. It's a way of turning this complex waveform into slow wave. So they found a few different things. Their first finding was that just on the slow wave detection, they detected no slow waves during wakefulness or during REM sleep. So Bernie, this relates back to is REM dreaming conscious. They did not detect any slow waves during REM sleep or during wakefulness. They did detect slow waves in all stages of REM sleep, with fewer detected during light sleep, remember these early stages of NREM sleep, and more detected during deep sleep, so these deeper phases of NREM sleep. And so that's what this is showing us here, is they're showing us how many slow waves were detected in each stage of sleep. So this would be wakefulness, then we have stage 1 and 2, kind of light sleep, and then Remember, the stages have changed, so these 3 and 4, when this paper was written, would still both be deep NREM sleep. So an increase in the number of slow wave cycles depicted, and then this is a depiction of how long of an interval there was between detecting those. So that was finding number 1. There are more slow waves during these deep sleep NREM stages. Great. We've established that these slow waves do seem to be specific to deep NREM sleep, or to specific to NREM sleep and more prevalent during deep sleep. Next, what they found was each slow wave cycle affected a varying subset of EEG channels, with most of them affecting 30 to 50 channels. And in fact, slow waves were much more frequently detected in some electrode areas, and there are in some areas than in others. So that's what we're seeing here. Is this is taking one participant and it's looking at different slow waves that are detected. So these red arrows are referring to a specific slow wave that was detected and how many electrodes or channels were affected by that slow wave. So we can see one here was kind of more in this back area of the brain, and it affected 17 channels. And then there was another here that was more frontal, right frontal, and affected 46 channels. And then this one that affected 87 channels, it was across the scalp. So again, not all the waves that were detected affected the same channels or even the same number of channels. And then they looked to see, well, which channels were most likely to be affected by a slow wave. And they found that not all channels were equally likely to be affected by a slow wave. So some regions, some channels were more likely than others to be affected. So this is basically a heat map of which electrodes were most likely to be affected by any given slow wave. Where do you see the most slow waves? And they found that you see kind of this hot spot in frontoparietal regions, mostly frontal regions, where you're detecting more slow waves than you are in other regions of the brain. So we're seeing slow waves are specific to NREM sleep, more frequent during deep sleep, and not every wave is affecting every electrode. So it does not seem to be a whole brain wave every time, right? Different subsets of electrodes are affected by different waves. And there are certain regions that are more likely to show slow waves. So now we get into the question of, is this a traveling wave? And the short answer is yes, it appears to be so. So each cycle of the slow wave oscillation, so each slow wave, appears to propagate as a traveling wave, meaning that not all electrodes are affected by any given wave, and not all electrodes that are affected by a wave are affected at the same time. So the wave is detected in some electrodes before others. So that means that this wave has an origin and it has a direction. So it starts somewhere, slow wave starts, spreads throughout the brain.
And does that set of origin change?
It does. So it doesn't always have the same origin. It can start anywhere in the brain and it can propagate in any direction. However, that is a very good question, Ilian. It leads us right into the next, that there are some sites that are more likely to be the origin than others, and some directions that are more frequent than others. So although these slow waves can originate and spread anywhere, and they do, they most frequently originate in anterior, meaning frontal regions, and propagate posteriorly. So they most often start in the front of your brain and propagate back. And that's kind of what this is showing us here, is several different wave patterns. So this one started at the red star. So here's the wave. And then we see that it starts at the red star and propagates back. A different one started and propagated back. For those of you who aren't listening, we're basically just looking at depictions of different slow waves that were detected in this experiment, where they started and where they propagated. So the color is the shade. Here's the time in milliseconds of where it was. So you can kind of see this rainbow effect of this wave starting at a specific location and spreading over time across the scalp. So what that tells us, again, is that they travel, but like you asked, Ilian, there's a really insightful question. Although they start and spread in many places and many directions, they most frequently start anteriorly and spread posteriorly. And importantly, these patterns
So
were
they
not
go
just...
from front to back, right?
Exactly. From the front of your brain is where they most often originate and then propagate back. But not always, just most often. And this appears to be consistent both between subjects, so it's not just one person's brain did this, like all of their participants appeared to do this, and it also is consistent over nights. So remember, participants came in for 2 different nights, and this pattern was consistent on those different nights. So that's our summary. They actually get a lot into what the mechanisms of this might be. It's super interesting. I recommend reading this paper if you want. It's Massimini et al. 2004 in the Journal of Neuroscience for that citation. But those are kind of the overall major findings without getting too deep into the nitty gritty. So Ilian, I know I'm going to go onto the slide. I know you have some questions for Bernie on this that you got into, and then I jumped in to give more details on the science, but now we can talk about the ideas.
Yes, I love discussing the ideas. So as you were going through the paper, I did notice that you talked about some things that we previously discussed in episode 1 and 2 of this discussion, such as the dynamic hub of things. And I just wanted to ask Bernie to elaborate a little more on how this paper ties up with global workspace theory and its features.
Well, global workspace theory as a theory is probably oversimplified, just like Newtonian theory of the planets and their orbits and so on. At a very fundamental level, going back to Newton, is really oversimplified because, after all, Newton didn't really know about the details of the surface of the moon and all those kinds of things. And that's what framework theories usually do. You don't want to go to them for the details. You want to go to them for the overview. And GW, Global Workspace, is really an overview, really a framework. And there are any number of theories, very, very good ones very often, maybe let's call it a dozen. I'd like to call it a family of GW theories. And there's some wonderful work by very good scientists who have kind of built on the basic foundation and done really excellent work so that there's a coherence in these dozen theories. And I like to talk about the GW family and basically use GWT as a way to talk about the fundamental framework. And this is a point that has been made by others, of course. If you think about it, you need to get your conscious hearing, the conscious things that you're listening to, from the auditory cortex, which is in a somewhat different place right next door to the visual cortex. But you get profoundly different experiences. Vision is different from audition, although they interact naturally because we live in a world where visual information comes to us and auditory information comes to us from the very same bird that's chirping in a tree. And we have to reconstruct that from the sensory information. So this has been thought for a long time. And so you have to think of GWs, global workspaces, as kind of traveling from one place to another, from auditory cortex to visual cortex in the brain, and the broadcast taking place from there, or maybe taking place from auditory cortex, let's say for hearing, in combination with the prefrontal cortex, which has all kinds of higher level integration going on. So it's kind of a hierarchy in a sense. The prefrontal cortex, let's call it the highest level of the hierarchy, and auditory stuff certainly goes up there. And then you can actually look at both auditory cortex and prefrontal cortex to get the whole story. Same thing with visual cortex. In most realistic situations, the two are working together to give you your interpreted visual sense, not just your raw visual stimuli, conscious visual stimuli. So the plausible idea here is that this broadcast, in a sense, is running around the brain, and it can go to different places, or maybe it can combine different sources from different part of the cortex, and then broadcast to the rest. And that's at least a plausible guess. A number of people have suggested that, and I think the idea probably goes back to Aristotle, who wrote beautifully about these things, but didn't have much brain science. But he knew about the brain, of course.
Yeah, I think that's really interesting, Bernard. Go on.
You go ahead.
And so I think that's really interesting in that the idea of broadcast and build, and you mentioned a few important things here, the broadcast piece and the information integration piece, which is something we'll get into in this next paper, are really important for conscious experience. And when we saw the slow wave, it was actually specific to parts of sleep that don't involve dreaming and was specific to not wakefulness. So it was something that we're seeing specifically not during consciousness, and yet we're seeing this kind of traveling wave. And so I think it maybe tells us something about, and this is one of the things I speculate in the paper, about the actual kind of functional setup of the brain, a basic architecture of...
So what does the word functional mean, Aaliyah?
Oh, that's a good question. How the brain functions. So if we're talking about the brain, we have structure. So the actual what is physically connected to what else through white matter tracks, which are assemblies of neuronal axons. They send their little signals down. So we have the cell bodies, we have the axons, and we have them all connected to each other, and that is the structural connectivity and the structure of the brain. However, neurons don't just talk to other neurons that they're directly, physically, structurally connected to. So we actually also have this idea of functional connectivity and the function of the brain. So how do we actually see fluctuations or changes in what brain regions are active together, how these, in the case of EEG, waves are propagating, and to really understand what's going on in the brain, at least in my opinion, you need to understand both. You need to have a sense of the structural architecture, but also the functional architecture, and there's not always a one-to-one correlation.
Right. I've come to like the city metaphor for the brain because it has neighborhoods. Cities have neighborhoods. Cities have traffic flow. And during morning rush hour, the traffic flows in one direction. And during rush hour in the evenings, they flow in the opposite direction in the traditional way of looking at things. And that is important because it's not just location, location, location. It's also location and flow, location and flow, location and flow. And once you start thinking that way, by the way, a lot of neuroscience, which sounds very heavy, right, makes sense because a lot of it is really common sense.
So, Leah, that was a very nice discussion we had on the first paper, and you gave an excellent summary of it. Can you do the same for the second paper? Just summarize it briefly, the findings, what were they looking for, the methods?
Yeah, absolutely. I would love to. So this next paper we're going to discuss is a little bit more obviously or directly related to consciousness, and it is called The Breakdown of Cortical Effective Connectivity During Sleep. Now, this effective connectivity is a specific term, so we'll talk about that in a minute. But this is again by Massimini, who is the scientist who we gave an overview of his bio and research at the beginning, as well as his collaborators Fabio Favarelli, Rito Huber, Steve K. Esser, Harpreet Singh, and Giulio Tononi again. So this paper starts with the observation that when we fall asleep, our consciousness fades, like we talked about going into the NREM sleep, but our brain, like we saw in the previous paper, remains quite active. So they set out to understand why that is. And their hypothesis is that it's due to changes in information transfer. So this active brain with fading of consciousness is because of changes in information transfer. So what does that mean? Basically, information transfer is what it sounds like, kind of the passing of information throughout the brain. For example, like Bernie was talking about earlier, from our sensory systems, which we're processing information about external environment, to our memory systems, where we encode that information, or frontal or decision-making systems, where we decide what to do about this information we're receiving. And so this ability to transfer and integrate information across multiple brain systems requires something called effective connectivity. So this is the ability of firing of neurons in one group, so firing of one group of neurons to effect the firing of another. So one group of neurons fires and it causes changes in the firing rate of a different group of neurons. So that is effective connectivity. So why would that matter for consciousness? Well, Massimini and his colleagues have suggested that consciousness, and this is very similar to global workspace theory, so they've suggested that consciousness is dependent on the brain's ability to integrate information. So if they were able to show that there is indeed a change in information transfer during these non-conscious phases of sleep, that would offer evidence toward their hypothesis that it is information integration that is kind of the feature of neural brain activity that is directly related to consciousness. So how did they go about testing this? I'm going to, for those of you following along on the screen, share my screen here. And for those of you who aren't, I will describe what we are looking at. So they combined two different methods to do this. They combined EEG, which we talked about before. Remember, EEG is we're recording the fluctuations of these electrical changes at the scalp, with something called TMS, or transcranial magnetic stimulation. So again, in EEG, we're not putting anything into your brain. We're not affecting the activity in your brain. We're just recording at the scalp what is happening, what the electrical activity in your brain is. TMS actually changes that activity. So transcranial magnetic stimulation can be used in a number of different ways, but it can induce neural firing or it can prevent neural firing, depending on how you deliver these pulses of magnetic stimulation. So in this, they use TMS to induce neural firing in a specific region. So they chose the prefrontal cortex and on the right side for a number of reasons. Yeah, Bernie, jump in.
Well, I think it's the premotor. Is that right?
I think you're right. Yeah, sorry, premotor. Did I say prefrontal?
Yeah.
Sorry, premotor cortex.
My question when I read that was, why?
Yeah, so they said that they chose this region because it's an area that is highly connected. So in theory, it's a region where the firing of these neurons should result in firing of neurons in other brain areas because it's a highly interconnected region, and also practically one where you can deliver this TMS pulse without causing a huge artifact, which can be a big issue if you're doing TMS and EEG together. When you deliver the pulse, there can be a huge muscle artifact that completely contaminates your EEG and makes it hard to see the brain signal. So that's an excellent question, Bernie, and their methods, that's what they said.
So here's my puzzlement for these authors. This is not to put you guys on the spot, but the authors, of course, they may never find out about this, but anyway, my impression from the Penfield work, 1,200 surgical subjects studied over maybe, whatever it was, 30 or 40 years at the Montreal Neurological Institute, absolutely the most spectacular stuff and the most fundamental stuff that I know. And it was early on, right? I don't think they got enough recognition, really. Anyway, so my impression from Penfield is that stimulation to premotor cortex does not become conscious, or maybe I should say this, it does not become conscious in a sensory way. Now, I do not know if that is correct, but when I looked at the Penfield and Roberts book, that kind of leaped to mind.
Yeah.
So I'm curious about that.
That is really interesting. And they're not studying, they don't ask people in this paper about their conscious experience. So they don't say, were you aware of this pulse when you were awake? So it is missing the kind of subjective report piece that is important to consciousness. They're here kind of purely studying the brain dynamics between...
Yeah, let me complain about this. It is absolutely baffling why in 2021, when everybody by now should be okay with the idea that sensory events, most of them are conscious, maybe not all of them, why do people not simply ask subjects? And I think actually, I'm not supposed to say this, but I think scientists have made major errors, and I can actually point some accusing fingers, but I won't do that, of major errors that have entered the field because in one way or another, people are still physicalistic reductionists. And that's okay if you're studying molecules. It's not okay if you're studying consciousness. You have to find out what the person is experiencing.
Yeah, and I wonder how much of it is part of the kind of baggage of the history of psychology trying to become a hard science and like considered a hard science where we're like, see, we can prove it. And we forgot that we're studying humans and their experience.
Well, good. This gives me an opportunity to get on my bandwagon because the sensory sciences are very, very solid. We now know a lot about sensory physiology as well, of course, all the way up to the cortex. And people still talk about sensory experiences as if they are subjective. But the word subjective has at least two meanings. One of them is sort of flaky, sort of, it's not really stuff you can believe. And my bandwagon speech is that every electronic gadget that you have to listen to audio or see video or get vibratory feedback from your cell phone when you're pushing the button, and probably all kinds of other things, are perfectly reliable, trustworthy, theoretically interpretable, all that kind of stuff, the normal criteria for the concepts that enter science. So for some reason, scientists are supposed to be on the frontier of everything. And on this particular frontier, they've absolutely gone missing. And so much for my, for my hand waving.
No, I think it's something really important to consider of like losing sight of the forest for the trees. Missing out on this core piece that is the experience. And so that is a major limitation of this paper is not only did they not ask people about their conscious experience, but as Bernie points out, which I didn't actually know, so thank you for that, this area that is being stimulated is apparently a region that, according to Penfield's experiments, people were not conscious of the stimulation of in other experiments.
Right. And don't forget to check that because I'm not sure if it's true.
So we'll put a little note to fact check that. So I think that's really important is that here what we're looking at, it is a study of the brain dynamics during different stages of consciousness or different states of consciousness. So during the transition from wakefulness to non-REM sleep. So we're looking at brain dynamics during these different states of consciousness, but we're not looking at conscious experience per se. And I think that's a really important distinction. So thank you for making that point, Bernie. And so, methodologically, what they did is they looked at the transition from waking to sleeping, and they had people once again in the lab falling asleep with EEG on their head, and they would deliver this pulse of TMS to the premotor cortex on the right side. And so if you're looking at the picture I have up, this is a plot from the paper. The red lines represent a TMS pulse, and the ongoing black lines represent the recorded EEG from the electrodes. And so what they do is they deliver this TMS pulse to this specific location, and then they look at how that propagated throughout the brain, how it influenced the recorded EEG activity. And what they found was a pretty striking difference in the waveforms, the EEG waveforms, following this TMS pulse in different stages of wakefulness and sleep. So on the left-hand side, if you're looking here at the PowerPoint presentation, is essentially a kind of a heat map that we'll use to depict brain activity. It's a little bit tricky to understand, so we'll focus mainly on the right side. But very briefly, as you go down this axis here, you're looking at trials. So there are 450 trials represented. So this is basically like a grid that's been kind of faded. You can think about it as an XY grid. And as you go down, you're moving through trials with each row representing a trial. And as you go across it, you're moving in time through that trial. And also, as you're moving down these trials, you're moving from wakefulness into different depths of sleep. And so we kind of have a heat map of how much activity is going on. That they have over here transformed to a waveform. So again, the red line represents a TMS pulse. And remember, this TMS pulse induces local neural firing at the location that you deliver it. So in this case, the right premotor cortex. So what we see is the recording of the response of an electrode at the place where they're delivering the TMS pulse. This is not across the brain. This is just local in the premotor cortex. The response of the neural assembly at that location to this TMS pulse. So during wakefulness, the pattern we see is this kind of initial response and then a number of kind of equal in size waves that eventually fade. So we see these oscillations, these waveforms, and they're both many of them, and I mean, they're not small, but they're kind of equal in size and they slowly fade over time. So we have kind of a ongoing waveform. As we move into stage 1 sleep, we see an increase in the size or the amplitude, the height of the initial response. So a greater initial response in these local neurons, or at least in the recorded response. Remember, we have volume conduction, but we're hoping we're getting a stronger signal right under this electrode. So we see an increase in the initial response, but then beginning of a fading. So we don't see as many waveforms to follow. We kind of see a larger initial response and then fewer responses that follow, fewer waveforms that follow in light sleep.
Can I ask my carping question?
Yeah.
So we're talking about animal cells
Yeah.
that you're picking up the activity of, their neurons. Some of them are inhibitory, some of them are excitatory.
Yeah.
Some of the heat certainly reflects cellular activity in the surrounding tissue, right?
Yeah.
Because there's all kinds of support cells.
Yeah.
But the heat only picks up thermodynamic, what's it called? Exothermic chemical reactions, essentially. I think that's right. And so we're not sure, maybe we are sure, but tell me about that.
Are you talking about the heat map, Bernie?
Yes.
Oh, so that's not actually, that's not actually temperature. That's a way of depicting activity. So it's just the brighter red colors are their rate of neural firing. There is an amplitude. So you can think about this as a 2D wave. This isn't a temperature measurement. It's a depiction of the amplitude of the response.
Yeah. So there's excitatory neurons and inhibitory neurons.
Right. So you're saying we can't distinguish between the firing of excitatory and inhibitory neurons.
Well, it's really a question.
Yeah.
So that's it. It's just a question.
Yeah, I think that's a really good hypothesis for what, could be going on here. I'm going to quickly describe, as we get into deeper sleep, we see an even larger initial response with basically no waves following it. But as Bernie pointed out, there are neurons that are excitatory, meaning their firing will generally cause greater firing in the neurons that they connect to, and they're inhibitory neurons, so their activity inhibits the activity of other neurons. And here, we can't distinguish between those. We don't, and this is true for any EEG, right? Or any of this electrophysiological recording, unless we know what neuron we're recording from and what the function of that neuron is, we can't distinguish between excitatory firing and inhibitory firing unless we then see the effects of it. So it could be, different assemblies. When we see these kind of changes, we don't know how much of that activity is excitatory, how much of that activity is inhibitory. In this case, since it is induced firing, we would assume that there shouldn't be a difference in the neurons that the TMS pulse induces to fire during wakefulness versus during sleep, because it's forcing them to fire. They're not getting input and then from other neurons, then communicating that along. They're getting a physical external pulse that's physically forcing firing. So
you have to take into account, if you look at a cortical column, the typical one, you see the pyramidal excitatory cell with a long axon, which is really important in terms of the question of consciousness, because Robert Kozma, for example, argues that the long branches, the axons, are really a fundamental thing in terms of consciousness. And that makes sense from the viewpoint of GW and related theories. But the long pyramidal axon is surrounded by little inhibitory, what are they called? Well, anyway, you can see them. They're like little ants around the wire of the long axon, and that's the typical cortical column. There's cortical columns all over the place. But I'm not saying this contradicts your point, because there's all kinds of possibilities. There's global inhibition, all that kind of stuff.
Yeah, I feel like different neuroscientists study things at different levels, so we can get stuck in our level. I think that was like something that I took a class on the circuitry of parental care, actually, and that was mostly animal studies, but it was like kind of the first time my mind was blown. I was like, oh my God, right, that different circuits serve different functions and different neurons serve different functions. So when we're looking at the level of, what we're recording in EEG, that's one level of observing activity, but it doesn't give us insight into these other levels of like, okay, there's more or less activity, but like, what are the actual circuits doing? What is their function? Are they excitatory? Are they inhibitory? And you're absolutely right that we cannot see that here.
Well, we can't see it here, but we might be able to think a way around it, of course.
Yeah.
And maybe somebody else has done some studies on that.
Yeah.
This is not an all or none kind of a question.
Yeah, agreed. The takeaway from, this kind of first finding is that there is an enhanced initial response in both amplitude and its latency or duration in deep sleep compared to wakefulness, but that the sustained response that you observe during wakefulness of multiple following waves, and again, this is locally just under one electrode where the response is where the pulse is delivered, fades during NREM sleep. So where you have the sustained response of multiple waves during wakefulness, during deep sleep, you essentially have one large response and followed by a short refractory period, and then essentially no further waves. They also looked to see if this was true in terms of where we were seeing response. Remember that first finding is just in one electrode looking at its activity over time. So then they said, okay, what about the propagation of the signal over space? So over different areas of the brain, over different electrodes. So they had co-registered the electrodes with scans of these individuals' brains with structural MRI scans, and looked to see, okay, we delivered the pulse, and where do we see responses based on, again, these electrodes, which electrodes are showing a waveform after the delivery of the initial TMS pulse. And what they found is that you get a much more kind of diffuse waveform. And if you're looking at the picture here, dark blue is kind of time zero after the TMS pulse delivered, up to this red, this 300 milliseconds. So that can look at the spread where darker colors on the brain or more blue colors are kind of the initial response, and then the brighter pink colors are over time. So as the signal spreads in time and space. What you can kind of see here is similar spatially to what we saw temporally before, where in deep sleep, the signal stays pretty local. There seems to be this initial response in the waveform, and then not much else after that, versus during wakefulness, you see the initial response to the waveform, and then you actually see this propagating, like we saw in the previous study, except during sleep. But you see this during wakefulness, you see this induced firing propagating to different areas of the brain, which, if we get back to this definition of effective connectivity, suggests that during wakefulness, when these neurons in the premotor cortex are induced to fire, their firing then induces other neurons in other regions to fire. So we have effective connectivity, versus in deep sleep, we're not seeing that spread of the firing, which the authors interpret to be evidence that there's a breakdown, like the title of this paper says, in the effective connectivity of these neurons during deep sleep.
Right.
Go ahead, Bernie.
Sorry. I can't read the numbers right now. How far does this thing propagate?
How far in terms of time or in terms of spatial distance?
Well, actually, both of them.
So this, I don't know where the signal absolutely faded out to where it was no longer detectable, but this figure that I'm showing is looking at 0 to 300 milliseconds. So very fast, that's less than a second. So essentially in NREM sleep, we're not seeing much activity after it looks like about 100 milliseconds. We see kind of no pink there, versus in wakefulness, there are measurable EEG waveforms out to, I assume, beyond 300 milliseconds, but here they're just depicting up to 300 milliseconds. And by 300 milliseconds, it's kind of spread from the initial point of stimulation, both to other regions of the brain, but also, I think importantly, to the other hemisphere, which we don't really see at all in NREM sleep. So the corpus, there's a signal that's being transmitted, we assume, across the corpus callosum or other interhemispheric. Huh?
Yes, it always is going across the other hemisphere, because the two hemispheres are, if you look at the top-down wiring, it looks like a butterfly.
Yeah.
There's these beautiful, what would you call them, Aaliyah?
White matter tracks, right?
Right.
Is that what you're thinking of?
Yeah, I'm thinking about the ones that go across from left hemisphere to right hemisphere. And if you're looking down on the corpus callosum, you get this beautiful double fan.
Yeah.
Two wings of the butterfly. And I think it's true to say, but we always want to check, right, that there's point-to-point connectivity from just about every point on the left-hand side to another point on the right-hand side. Now, again, that may be an oversimplification, so let's keep it qualified. That's really important about the corpus callosum, because we usually tend to think of left or right hemispheres as if they are separate.
Yeah.
And they look separate, and we are suckered, right, by the sight of things. But then usually and historically, we get deeper and deeper into the weeds, and we learn to figure out the actual activity, the effective connectivity, as we're saying, and we see more details. So right now we're actually able to see specific neurons, which is going to be amazing.
Yeah.
So anyway, I just wanted to mention that.
Yeah, I think that's really important. So, here we're seeing during sleep a breakdown of both kind of this local effective connectivity, but also this interhemispheric transfer doesn't really seem to be happening, versus during wakefulness, you have this much more diffuse response where this initial induced firing is then causing firing in other regions that are both within the same hemisphere, but also interhemispheric, so in the other hemisphere of the brain.
Let me
yeah, go ahead.
Let me mention something, because I just love the idea of this paper when I first heard about it. And then I looked at it, and I was a little disappointed. There's another huge literature on the cortical activity during slow wave sleep. And the usual way of talking about it is that it doesn't look like a slow wave. It looks like buzz, pause, buzz, pause. And all the cortical neurons seem to buzz at the same time and then pause at the same time. Now, let's suppose that that is true. How would that influence our understanding of what you just said? The breakdown of, why don't you say it? Because you know the words better.
Yeah, so they showed in this paper a breakdown of this effective connectivity. So the ability of the firing of one group of neurons to cause another group of neurons to fire during NREM sleep. But Bernie, to your point, I think that's what the previous paper showed, is that even though it appears that all cortical neurons during NREM sleep are activating and deactivating together, that actually it is this kind of slow traveling wave with different originations and different propagation patterns. But what we're seeing here is that, even though that happens at this 1 hertz slow wave, when we're actually inducing firing in the way that, stimulation from the outside world might during deep sleep, we're not seeing that signal effectively propagated. So we're not seeing this effective connectivity to transmit or integrate this information across multiple brain regions during deep sleep in the same way that we are during wakefulness.
Bernie, here's a question to you. So what is this reduced effective connectivity during the NREM part of sleep tells us about consciousness. How does that tie up to global
Well,
workspace?
it's actually very interesting. And again, I'm not sure I'm up on the latest and greatest, but when I was around the Neurosciences Institute in San Diego, we had some people there who were recording directly from cortex in animals. I think rats, I'm not sure. But rats, certainly the pattern of consciousness, sleeping and waking, cortex, all that is, let's call it universal among mammals. So as long as you're talking about mice and people, it's reasonable to guess that you're talking about similar gross patterns, right? Not the fine patterns, because rats don't have language. But still, cortex is cortex. And so the question I would ask is, let's assume that the ground truth here is that you've got this buzz, pause thing going on at the neural level. And outside of the scalp, especially in humans, of course, that's not what we see. What we see is these slow waves. And so let's assume that the ground truth is the neurons, and that's an open question, of course. If all the neurons in cortex pause simultaneously at some point for maybe half a second, what's going to happen to propagation? You're not going to be propagating at all during the pause, assuming, of course, that all the assumptions are correct. And so I would expect there to be no propagation at all during the pause period of slow wave sleep, and to be a lot of happy propagation during the buzz part, but I do not know that. And so it's another question.
So you would hypothesize actually that the response would depend on the timing of, say, a TMS pulse, that if you timed it in sync with the peak of the wave,
Yep.
you would see immense propagation and no propagation if you timed it in time with a trough.
Right. There's only one additional link that we're inferring here, and that is that the timing of the scalp EEG tells us the exact timing of the cortical EEG. And again, that's a question that needs to be answered.
When you look at the findings and the conclusion of this paper, does that pass the sniff test for you? Does it check out? Are you like, yeah, it seems like there's a breakdown of this effective connectivity during deep sleep? Or do you think I need to see more evidence to convince me of that?
Well, if you're working with animals, for example, where you can easily do this kind of experiment, what you would do is simply record from the cortex, or from as close as you can get, to see where the buzz is and where the pause is. This is assuming, of course, that you get a single coherent buzz and a single coherent pause. And let's just assume that for the moment. What you would expect, of course, if there's no propagation during the simultaneous pause of all the cortical neurons in a mouse, let's say, because the system is completely stable and it's doing nothing, right? During the buzz, you have a huge amount of instability, and you want instability because that's what you're propagating your wave on. And that's what you get with waking activity. So that's a story that's worth considering. And let's just move on from there.
Okay. So I guess, Eli, I don't want to step on your toes here because I know you had some questions, but I think both of us would be curious, Bernie, to, when we talk about GWT, one of the big things we talk about is this broadcast and build, this ability to propagate a signal and to integrate information. So how does this finding of what appears to be reduced effective connectivity, what principles of GWT does that relate to? Does it offer evidence that supports GWT? Does it conflict in some way? Like, how do you integrate that?
Well, you have to remember that GWT and the whole GW family is a few basic concepts, right? With a lot of the specifics missing because we had no idea about the brain bases. Or some people might have had an idea about the brain bases because always some people ahead of the game. And they're very, very good, very respectable, wonderful people who managed to pioneer things. In any case, what you would expect, I think, is that during waking activity, background activity, is really very fast and very high and so on if you record directly from cortex. That's the time when you can propagate pulses, right? And that happens to be, waking period also happens to be the time when you're conscious of the world and optimally set up to respond to visual, to auditory, to any kind of sensory input, and to respond via any number of goal-directed motor actions. So that's what waking is for. And the weird thing about slow wave sleep is that it seems to mix these two states. Notice if you have half a second of waking followed by half a second of sleep. And I think people have asked that question. It's a very interesting question because it suggests that even during slow wave sleep, there might be half-second conscious periods. Don't know if that's true. So please go ahead.
Well, I just wanted to somehow tie it all together and ask you to do that, actually, Bernie. So for these past... Is that a hard no?
Well, there clearly is, if we assume that auditory cortex is in one place and visual cortex is right next to it, but it's a different place, and it's at least, 1 centimeter, or whatever the distance was that Massimini in this particular paper found their propagation of the TMS. And they failed to apparently stimulate, as you noted, they apparently failed to stimulate during the peak of the wave, which,
Well, we don't know. I mean, they stimulated multiple times, so I would assume or hope that some of the stimulation was during the peak and some was during the down, but they did not time it specifically to the waves, as far as I know. So it's an open question about what the timing of the any slow wave activity was in terms of the relationship to the stimulation.
Yeah, I think that's right. And you have to remember, of course, that we're talking about research that started actually in the 1950s when the term, what am I looking for? Paradoxical sleep came about through the early French research on this. And paradoxical sleep was called paradoxical because the brain looked like it was awake, but the body looked like it was asleep, right? And so that was interesting. And you've got the eye movements and so on. But that's the notion of paradoxical sleep for dreaming goes back to the 1950s. And it's a very interesting, I think it's a deep idea, it's an important idea for us to remember and see if it's true.
And so would that refer to like REM phases where you're mostly dreaming?
Yeah, this had to do with the discovery of REM. And I should remember the man's name in the 1950s who coined the term paradoxical sleep because he was recording eye movements, which are big and clunky, as well as EEG. And so the EEG seemed to show a waking brain and the body was asleep.
Yeah, and I think that's important to note that the studies we're talking about today, where we see what appears to be a breakdown in the effective connectivity and a slow wave propagation, that's during NREM sleep. So this subjective loss of consciousness versus, and like in the first paper, we saw that the slow wave activity actually disappears during REM, like it does during wakefulness, suggesting that there's different brain dynamics going on during REM sleep. And the second paper that we just discussed, I actually would have to look, the findings were during NREM. I'm not sure they looked at REM. They might, I'd have to look and see, but the findings reported are during NREM, not during dreaming.
Let's just remind our people, the audience, that NREM means non-REM, so there's no rapid eye movements, at least that's the idea.
Yeah, and in theory, not dreaming like we're talking about. It's kind of deep.
No,
sleep.
Actually, I think it's the other way around, because REM is associated. Oh, sorry. I think we're agreeing with each other.
Yes, yeah, I think so.
Right. Okay. Good.
Yeah, but I think Bernie, you're kind of pointing to, what they're trying to look at here is kind of the cessation of consciousness and the transition from waking to NREM sleep. And the point that you're kind of making is REM looks different partly because of the rapid eye movements, but also because this is where we have this kind of different experience of dreaming that might also be conscious. And maybe that's another episode of like what happens during REM, during this dream state. But here it's, really thinking about what happens in this ostensibly non-conscious period, or at least where consciousness fades from the waking state.
Right. The one thing, I gotta remember this man's name. I think I met him one time, who discovered this about REM and coined the term paradoxical sleep, because to him, he had EEG of the kind they had in the 1950s, which was nothing to write home about, right? But they had it, and they did the right research, and they came to, interesting conclusions. And this paradoxical idea is that the brain looks like it's awake, using the chroma EEG of those times. But the body, as you know perfectly well, is paralyzed. Looks like it's paralyzed, not quite paralyzed, but it's good enough. So that's very different from waking, when the brain looks awake and the body looks awake.
So if we take the results of this study to be, legitimate, what would that tell us about consciousness, Bernie?
Well, I think the evidence, these are very good people, and you can believe them, especially if you can find supporting evidence. Of course, we always want to find multiple sources, but I certainly believe them about this. And then you can ask additional questions. I wonder if the title suggests a grand hypothesis, and I'm not sure if the evidence supports a grand hypothesis, and that perks up my ears.
Yeah, thank you, Bernie.
Sure.
I think it's really very complex questions, and obviously, like everything in science, like not one that a single study or a single paper can answer.
Right.
But I do think it's really interesting to look at these shifts of conscious awareness or conscious states that sleep can give us a really good window into. And, so what we saw today is as we shift from wakefulness into non-REM sleep, we see this dominance of these propagating slow waves, and we see a shift in the ability of, or in effective connectivity, meaning kind of the ability, measured as the ability of a TMS pulse or induce firing in one region to affect firing in other regions, which suggests a reduction as we're moving from wakeful conscious awareness to what we assume is dreamless sleep, although they didn't ask participants if they were dreaming. So that's kind of an assumption based on the categorization of the sleep phase, but into this phase of sleep, this reduction in the propagation or effective connectivity and propagation of these signals across the brain. So kind of thinking about back to global workspace theory and the importance of this broadcast and build, this ability for a signal to go across through different regions, through these thalamocortical loops that we talked about in previous episodes, seems to be kind of some good evidence from sleep that actually really is an important feature of conscious awareness, is this integration of information across timescales and brain regions that are indexing here in terms of a propagating wave. Does that kind of tie back into GWT for you, Bernie? That's kind of how, correct me if that's not how you think about it. That's how I'm thinking about it.
It certainly does. You have to remember, of course, that in 1988, when I wrote the first book, the brain evidence that we had, there was actually very interesting evidence, but it was not nearly as good as the evidence we have today. So what happens when the field explodes, like the neurosciences have exploded, and cognitive science also, is that, it's like the forest, the population of trees exploding. And in the old metaphor, we may lose track of the trees. Let's see if I can get this right. Trees and forests, all that kind of stuff. Complexity, cognitive complexity for scientists and people interested in this field increases when we have 20 different wonderful methods for recording brain activity. They all have slightly different properties, and people do different kinds of experiments, and then you lose track of whether it's conscious or unconscious. So you have to constantly kind of keep track of these very fundamental things, because otherwise we are as vulnerable as anybody else to getting lost in the woods.
Yeah, absolutely. And I think an important thing to remember too here is we have these amazing methods that really give us some insight, and we're limited in the questions we can ask by the methods we have. So anytime we're looking at these, or maybe not in the questions we can ask, but we're limited in the questions we can answer. I think we're never limited in the questions we can ask, and it's important to keep asking the questions that we might not be able to answer yet.
Yeah.
Because that's how we get there. But I think we're going to go ahead and start to wrap up this conversation for today, and really appreciate all of you thinking about these big, deep questions together. And if there's anything that kind of final takeaways for today's discussion that we feel are important to have in here before we bow out and say good afternoon.
Yeah. I actually have a take-home lesson.
Yeah, I'd love to hear it, please.
If I may. This is to scientists, and it's very private, so don't tell anybody else.
Okay, shh.
Try asking your subjects what they are experiencing.
Yeah.
And maybe you'll learn something.
Yeah. The importance of the subjective, especially when you're studying consciousness. I think it's really important.
Bet.
Because consciousness is, after all, subjective, right?
Certainly the experience of it.
Yeah, it's so old-fashioned, it's so 19th century to ask people what they're experiencing and to take them seriously. But the 19th century has some things to be said for it.
Yeah. Yeah, I have a number of examples from this, Bernie, that we can talk about maybe some other time in our own research of meditation training and subjective felt shifts in experience that distinguish, that really clarify the third person data. The first person perspective can really be absolutely essential in understanding these third person perspectives, and to not lose the importance of the subjective personal experience for the kind of quote unquote objective, although are we ever truly objective data? So that is amazing. Thank you so much, Bernie. Thank you, Ilian. Thank you to our listeners for joining us for these many questions, some answers, which is kind of how I like it to be. And appreciate you spending this time with us.
Yeah, I just want to say thank you for everyone. Thank you, Ilian. Thank you, Bernie. This was very insightful for me personally, and a great conversation to be a part of. Especially thank you, Bernie, for having me as your guest interviewer. And I'm looking forward to future conversations. So
I really want to encourage you both because we're really coming to grips with things that people have somehow lost track of for, what is it, 2 centuries? No, it's only a century and a half, I think.
Well, it's an honor to share this space with you, Bernie. Thank you.
As promised, to show our appreciation, we are offering our listeners a 50% discount for any edition of Bernie's book on consciousness, science, and subjectivity, updated works on global workspace theory. Just go to shop.thenautiluspress.com, spelled shop.thenautiluspress.com, and be sure to enter the word books, BOOKS, in the coupon code box during checkout for that extra 50% savings. Of course, Bernie's books are available everywhere books are sold, although your 50% discount is only available in the Nautilus shop. If you'd like to discover more about the conscious brain and learn more about global workspace functions, please visit Bernie's new website at bernardbaars.com. And I'm going to spell that also, BERNARDBAARS.com. And thank you for listening.